Okay, so here's an example by hand. This very simple, non-realistic data set where we will try to see how we would find G0 and G1 for this simple exponential model. So I'm going to guess, I look at the data and you want to pick something reasonable as possible. You can use tools, you can plot curves until you find something that looks pretty close. Multivariable cases, it's going to be harder, but there's techniques and a lot of tricks. But for this one, we just look for something that looks like it might look like this. So I just thought, what about 6e to the minus 1 x? So, or 6e to the minus x. So when x is 0, it gives me 6, exact fit. When x is 1, it's 6 over e, so that's between 2 and 3, and etc. It's decaying. So we just try this just to demonstrate. So let's just see how this would work. So we can actually do this by hand in spite of all those scary equations with the summations and everything when it's this small. So, well, we can't do it all by hand, but we need the two partial derivatives. So xi gamma over d gamma 0. So this one is and df xi gamma d gamma 1. Well, it's this with respect to gamma 1, so this stays the same chain rule, though this comes down, so we get xi gamma 0. Okay, so that's those two. Okay, so now it's time to use the guess. So we have f0, we're calling it, is equal to, and you'll see all these things make sense once you start fx g0. And so this just means that I want to compute this function only replacing the gammas with the g's, the g0s, and the xi's actually put in the numbers they are. So I get a vector here. I'll write it with commas here. I get, if I put 6 in here and minus 1 in here, I have 6 times e to the 0, so I have 6. And then I have 6 times e to the minus 1, so I have 6 over e, and 6 over e squared minus 2. And I get something like 6, 2.207, and 0.812. And so this is like your first approximation at the y values. Now, what we want for our linear system is we want to subtract this, because remember, we had some linear thing, a plane, but we also had the constant term where we started things at. So we subtract the constant from both sides and we get y0 equal y minus f0. So it's just this difference here. So the first piece is 0. Second piece is 3 minus this. So let's see, that's 0.793. And then the second one is 1 minus this, so 0.188, something like this. Now, we don't really care, you know, the computer carry this out with arbitrary precision. We don't care too much about that. So, okay, so far so good. We need our matrix of derivatives now. So we have d, we'll call it d0. And, well, this is just the partial with respect to gamma 0 in this column and with respect to gamma 1 in this column. So it's just going to be this and this evaluated at the g, replacing the gammas with the g's and the xi's, filling them in. So the first, let's go down this column first. So if x1 is 0, so I have e to the 0, so this is 1. Next one, I have 1 here, and I have g1. So what's that? That's minus 1, right? So 1 over e. And now I have 2 and minus 1. So that's 1 over e squared. Okay. When I do this one, I have a 0 for the first one. X is 0, so I get 0. Next one, I have 1, 6, 1. So 6 over e. And here I have 12 over e squared. Uh-huh. Okay, I can find out what these all are. I don't think it really matters much to write these down. So I could put in decimals to make you like them better, but it doesn't really matter. I did go to this part for R anyway to do the linear algebra. So we have B0, which is the least squares estimate so for y0 equals D0 B0. This is the least squares estimate here, okay? So least squares estimate. So I should put hat here. Or let's make this beta 0. Beta 0. And then B0 is the least squares estimate here. Okay, so B0 is just D0 transpose, D0 inverse, D0 transpose, and Y0. Use the computer, obviously. And we get B0 equals 0.0343 and 0.2690. Okay, well that still doesn't give you much of a feeling, but you know that you're going to set G1 now equal to B0 plus G0. And now it should, because the G is approximating the parameters. So G0 was 6, so I get 6. So it's telling me to go a little higher here. So we can drop these. We're going to keep them in the computer anyway. And the bottom one just becomes 0.731 or something like that, right? Okay. Shouldn't that be negative? It better be negative, right? -1 plus this, so negative. And did we get the other one right too? The other one would be +6 plus, yes, so the other one's right. All right, so this is our new estimate at the parameters. We could stop here and we'd probably have a better model, better fitted model. Now, to test whether we made any progress, one thing you can do is take SSE for using the first Y0. So we'll call this 0. And this is just the sum of, let's see, yi minus f0 squared. This is really just y0. And I got 0.664 here. And then if I do SSE 1, which is the sum yi minus. Now, I need f1, and I didn't compute it yet. This should be here, right? F1. I didn't compute it yet. I almost have it because I have G1, right? So I have to compute F1. I'll do it here. So I have F1 is equal to Fx. And I just replace gamma with G1 now and see what we get. So if I do this, I'll save you too much of it, but I wanted to do these numbers so you could check kind of 6.034, 2.904, and 1.398. Now look, these should be close to the numbers, and they look closer to me. This is just a little away from 3, a little past 6, and this is off from 1 a bit, but what do you want, you know? So this is this. So our y1, is it y1? Yeah, y1 is just equal to y minus this, right? So I have minus 0.034, positive 0.096, and negative 0.398. And so SSE1 is the sum of these squared. It's the sum of these squared. If I do this, I get 0.168. Okay? So the key is, and one thing you can put in your algorithm is to check that SSE1, SSE1 is less than SSE0. SSE2 should be less than SSE1. All right, well, I don't want to go too much further. What we do now, we plug in G1 to get G2 exactly the same way. If you do that, if you want to do it for an exercise and check your answer, I didn't write down G2, but I did write down SSE2. So it does improve again. SSE2 is equal to 0.148, okay, if you do it again. So you just repeat using 1 and 2 instead of 0 and 1. All right, so this concludes talking about this algorithm. The main thing when you use the computer is they want the start values. They want G0. It helps to give G0. Some programs figure it out, others don't, so it's important to have a strategy for this. So let's see, I can't quite figure out everything we need to do next, but it's going to sort of continue in this space. We definitely want to make inferences on the parameters now, okay? So this is part of it. This is where we're going. This will be the next lecture. So it's almost midnight. It's just midnight now, Friday night, April 17th. So on the 18th, I will have some more lectures, and by the 19th, I think if there may be a straggling lecture or two, maybe some R demos or something, and that'll do it. So just a few more. There's only a few more, really. We want to make inferences on the gammas now and have our nice nonlinear model. And that's about all we're going to do with this. So I hope it sort of widened your view of linear regression. But I'm not really ready to make closing remarks yet. We have a little more work to do. So, okay, take care. Let's get ready for the next one tomorrow. Bye.